Good afternoon. It's my pleasure to welcome you to a seminar by Dr. John Tester. He is Associate Professor in our General Basic Engineering Department, and he's also Director of Master of Science in Engineering Management. He joined us this August, and he's presenting a seminar as part of our new faculty seminar series. Dr. Tester comes in with very diverse and rich experience and background, both in commercial and military sectors, as well as mechanical design engineering and manufacturing processes engineering. He has also worked a lot as a system engineer. Of course, he comes to us not from industry at the moment, but he comes from Northern Arizona University. That's where he's taught for many years, and his experience and education guide his research and teaching efforts in areas of both design and manufacturing processes, with intent on improving the connection between the two. So we are very excited to have him here, not only to help us with our MS program in engineering management and programs in general and basic engineering, but also I believe that his research interests, which include design for manufacturing, rapid prototyping, injection molding, and engineering education, will be quite fruitful here. So with that, I turn it over to Dr. Tester and look forward to his presentation.
Thank you. So as it was noted early on, about 10 or 12 slides in, I have a break point where I could either continue with the presentation in an extended format or jump over some things. And so don't hesitate to ask a question if you want to. Being a Zoom format, it may be difficult for me to recognize it at the time. So apologize if that happens. So the title was, I had to give it something. It's M4D, Manufacturing for Design. And the 4 comes in here, putting in as a number 4 instead of FOR. And I'll just go into why I call it that. And it comes in about halfway in the presentation. And this is me at my former university, Northern Arizona, and in the background you can see some PPE that we were making, face shields, and I was wearing it as well. I actually started here at Tennessee Tech in 1983. I graduated. I was a radio DJ for WTTU, and I ended up with a degree in mechanical engineering and became an Air Force officer to boot. It's a whole different story. I also earned a Master's of Science in System Engineering and Logistics at the Air Force Institute of Technology and a Ph.D. in Industrial and System Engineering at Virginia Tech, both emphasizing either mechanical design or aerospace engineering. After my degree in Bachelor of Science in Mechanical Engineering, I was in the Air Force and served as an engineer for about 9 years. I did a variety of things. Project engineer, materials and processes engineer at a logistics agency, and a systems engineer at the very end, doing reliability and availability assessments on a lot of different deployed systems to the Air Force. The most prominent was the GPS systems that were then deployed, the satellites. I got out of the Air Force and served in Amtech Systems. I had a job there as an engineer, product design and tooling engineer as a startup company. And that was an interesting experience, but I decided to go get a doctoral degree at Virginia Tech. And once I earned that degree, I started as an associate professor, eventually becoming a professor at Northern Arizona University, ending that service this year. And then I came here. Associate professor, from August, as noted earlier. And my first half of my job as associate professor of general and basic engineering. The second half, the director of Master of Science in Engineering Management. And the third half is continuing and expanding research from the previous experience. And that's what this is about, is discussing my desires to continue doing scholarship and research here at Tennessee Tech. A little more on my background, and I'm bringing this up so that you understand my motivations for my research. And I should point that a lot of this is applied research, and that's where I tend to land, is in applications of investigations. I founded these two labs at NAU. They had my name on them. I had to sign off on everything. And the Rapid Lab was one, and it's over here in the upper corner. And it was a support resource for researchers on campus, but also for educational research, educational work, I should say, classes. It did a lot of senior design support across all the discipline areas. And it had CNC programming in addition to additive manufacturing services. But one of the things that's important to recognize is that most of this service was involved in the design process, not necessarily making things. Making didn't take much time at all. It was the design leading up to it that was the real service, especially to the researchers on campus who were in science. I also started the Mechanical Engineering Manufacturing Lab. I'll explain why I did that later. I would like to say instrumental, at least helped a lot in providing assistance for these other resources on campus during my time there at NAU. The Maker Lab is exactly what basically is here at Tennessee Tech, and it's also exactly in their library, which I found fascinating. It came about that way about the same time. It doesn't have as much variety as the Tennessee Tech's lab. Tennessee Tech goes into other things besides 3D printing. The Human Performance Lab is a biomechanics lab for anthropometric research, particularly towards human-assisted robotics. Basically, what I did for my last sabbatical was install the cameras and the computer system. Computer system you can see here, the cameras, you can only see a little tiny one right there, so that's what I did. Okay, a little more on the research I did. I did power prosthesis control using biology-based muscle theory. And you're wondering, how did I get to that from additive manufacturing and other design support? Well, that facility, the rapid prototyping, the Rapid Lab, supported a variety of researchers across campus, and biology was the biggest research group on campus. And I made some connections with several biologist professors, and one was investigating muscle theory, and so we managed to get several NSF grants together. I was the PI on a couple. To reprogram a powered prosthesis for using Dr. Nishikawa's biology muscle theory. And it worked fairly well for having never done it before. Here is a lab that was at ASU we had to use for a while until we got the Human Performance Lab. So that's sort of how I fell into that. And a couple of students I had with Dr. Nishikawa and the test subject, it's hard to see, but that's the prosthesis we were working with. And you had motion capture and all that. So I actually worked in biomechanics, mainly because I was the only automation thing close to an automation engineer there, or certainly a system engineer. Then I also did some design work, what I was very comfortable in, which is electromechanical design of a environmental field assay system. It would check on environmental contamination in open water sources. Another thing I undertook right before I came here was to be a part of the Arizona Additive Manufacturing Research Consortium. It's a lot of words for not done as much as it could have done. But basically my thing was 3D printing on Mars. I just used that as a title, and they actually bought it. They let me do it. Basically making highly filled polymers. I can talk about that at the end if somebody wants to. I got a couple of slides on it. I think I have one slide I can dig up real quick. And basically we used hobby extruders for 3D printers, and then we pour sand into it at certain measured amounts to get highly filled materials. And the nice thing about that is that with the hobbyist level, they weren't that expensive. You could tear up the screws and the barrels and just remake them very quickly, and it wouldn't cost much. And one of my design initiatives, what I wanted to do was to redesign the way screws were designed for the extruders to take care of this highly filled material, because it would rip the flutes right off. And then I brought this in at the very end, the Hewlett Foundation grant, Engineering Schools of the West initiative. Its purpose was to have regional outreach and to improve underrepresented students' access to engineering. And we were in the Navajo Nation area, also the Hopi Nation. And so I did some work with that. It was very eye-opening, but a lot of it dealt with engineering education and redevelopment. And D4P was the engineering education program that I'm going to talk about next that was supported by this. Engineering The engineering education program at Northern Arizona was designed for practice and referred to as D4P, the number 4. So now you understand where I'm getting M4D, because I started working on this proposal right before I left, and I got permissions from everyone to just use this. It's not trademarked or copyrighted. And basically, this program was design-oriented very heavily. Undergraduate education had integrated disciplines and very team-oriented. And what I brought to it from the funding that we had was to keep students from being intimidated by huge teams, which they had at the time of 15 to 25 students trying to design a system, into small teams to start with of 2 to 3 students, and then work their way through different quick projects till they got comfortable with that, and they would be combined into larger teams and yet larger teams, finally into one large-scale team for the final project. So you get a lot of systems-oriented organization that way. It worked fairly well. The downside was there wasn't much fabrication, and this is an example of that. This is the type of product we'd make. We'd start with Legos because we had not much at the time manufacturing capabilities, and so we use Legos and branch off of that with benchtop electronics and control systems and that sort of thing. And that's what made me want to start the manufacturing laboratory there, and also there's an advanced CAD/CAM lab and rapid lab at some point. So that's sort of how I got started into the manufacturing side of things in depth in education. As I mentioned, in 2020, actually maybe 2019, I started looking at developing a new concept for manufacturing and design. It would be called, instead of design for manufacturing, it would be called manufacturing for design. Basically, and I'll get into this later, it would deal with the design fundamentals of additive manufacturing, breaking out into traditional manufacturing processes, addressing engineering design at large. So mixing all that together. It's not strictly designed for manufacturing, it's also addressing manufacturing education. So it does sort of everything at once. Now, given that background, here's my research objectives at Tennessee Tech. Fundamental research I'd like to begin and continue here would be to have design for additive manufacturing, which is a field it's out in the scholarship area today. It's called DFAM, and I'd like to pursue further development of the DFAM context, and you'll see what in a minute, and other related objectives. If we have time, I'll go into it. I don't know that I will have time. That's why I left it blank. And then the other thing, and perhaps I should have put this first, is the research objective of engineering education. And the first one's where most of the research is developing the M4D course, program, what have you, with external support. Before I go further, I wanted to point out that I've only been here a short time, and so I've got these ideas for education. I've recognized that I don't know how the administrative process at Tennessee Tech works from the bottom up to the top in terms of developing courses, integrating ideas into existing courses, and so on. So if you hear something I say, don't be concerned I'm going to take over or something. I do not want to do that. But these are my ideas, and so I'm going to see how to create paths to make that work without impacting someone else's work. The other thing I want to talk about in engineering education briefly is the MSEM program and general engineering, developing courses and expanding however is needed for our department and our college. Mentioned this term several times, additive manufacturing. I wanted to set the context for what I'm going to discuss next. Additive manufacturing is beyond 3D printing. Consumer 3D printing with these cheap machines under $2,000 or $4,000 or less, that's not what I'm talking about, what I'm referring to. I might for some of the course research, but the academic research and class materials, but not for the theory aspect of additive manufacturing. I'm talking about the industrial versions of layered additive manufacturing. It may include blended materials, but most of the time when I look at scholarship on this and I refer to it, we're referring to metal printed products, which means that they are printed products that are ready for commercial application fully functional for the design use of the engineer. But there may be polymer versions. Some people refer to them as metals and polymers, blends and composites as well. And perhaps incorporated into additive manufacturing research in terms of design and manufacturing are the new processes that are still being developed. My goal is to address it in two ways. It's designed for additive manufacturing and also as a tool in engineering education. Forgive me for a second, I need to adjust my Zoom because I've got some views that are blocking my notes on another slide. Okay, it's another screen, here we go. Sorry about that. Okay, so what's my motivation here for additive manufacturing? Has that already been done? Well, it has in a way. It's already used in industry, and I'll just give you two brief examples here. NASA's Marshall Space Flight Center, I worked there for a summer. But coming back to that, they have a turbine engine pump. The housing here is created through additive manufacturing metal product, and it's used in their research. So it's very expensive, very time consuming to investigate, but they built it and it works. At the other scale is this company here, Imperial Machine and Tool, which is a machine shop, job shop. They're a machining company who recently acquired SLM machines, selective laser melting machines, what used to be called selective laser sintering, though technically it's not sintering. And they're making metal products just like they make to order machined metal products. And so additive manufacturing is already here being used for engineered products in industry at all levels. That's my point. How you design for that is catching up. Vendors who make these machines and software who serve the CAD design for these machines are doing bits and pieces of the design for process, but it's not complete. So there's still plenty of research in the design methodology for additive manufacturing. These are just some links there if you can get the PDF file for it. This is an example of part design, what's going on now, and it's actually fairly restrictive, though it looks really good. I need to start this, and then I need to, I believe, swing to another screen and bring it over. So I'm going to see if this works. There we go. This is a movie. I don't really know how else to do it, but just to show you full screen. It's from both GM, General Motors, and also Autodesk. It's a video showing Autodesk's, I forgot the name of the software. It comes up in a minute. Their software for additive manufacturing, and this is their design process, reducing weight and keeping the strength, and they're looking at iterations, and they're going to make a bunch of these. And so this shows where it's going to go into. This bracket's actually created from a larger assembly. I've got to stop this for a minute just to show you something. Wait till it's finished. And I just find it amazing. I am an additive manufacturing supporter of this sort of thing. But when you hand off stuff to marketing, it's amazing. They got it wrong. You can see the layers on this thing. It's actually built in this direction and not to this direction. So this is just one good example of telling students, don't believe everything you see just because it's in a video. But nevertheless, this was used in assembly. And it's this bracket here, which is in itself an assembly. And so the savings, probably not so much weight, though there was some weight saved, but probably mainly in terms of assembling that subassembly. And then another question I would ask if I were looking at this in a class or just as using this software is, this was a symmetrical seat, so people are sitting on their side. Why is this an asymmetrical product? And so what's the load path for these systems and so on? And so I don't think the software is quite there yet, though it is very impressive. Now, design for additive manufacturing, the design methodology approach, most researchers break it down in these three areas: system design, part design, and process design. System design is not the functional design. It's looking at the system you're going to manufacture. And then what you want to do is to say, which one of these parts am I going to create for 3D printing? And honestly, for my money, this is the one that needs the most research. How do you evaluate a physical system that's in either conceptual stage or a near first article stage, and then judge which part needs to be turned into an additive manufactured part versus which parts need to stay in the traditional manufacturing. There's also part design, which you just saw in the previous slide, and that's pretty traditional. That's going on a lot now, and software companies have that cornered pretty well, though they don't have all the analysis aspects. They're getting there. It's tied into a lot of FEA and weight analysis and also heat dissipation. Process design is not designing the machine itself, the machine process and changing it, but what are the process parameters to make this part have high quality given that you did the part design. And of course, there's iteration back and forth with all of these, mostly associated with costs and can you do it or not. Now, since I haven't had any questions, I think I've got time to leap forward and look at this briefly, more in depth about the theory, the design theory behind design for additive manufacturing. So I'm jumping ahead here a little bit to some backup slides. You can characterize design for additive manufacturing as either part design or process design, and I mentioned the system design, and I think this is the part that's missing. If you look at the research on this, and you can go back a ways, it really doesn't get much farther back than probably this century, the start of the century. But basically, these folks look at the manufacturing side and the design side. Almost no one addresses the system side. I will say that this fellow, I won't butcher his name, but trying to pronounce it, but he's looking at the entire process, but he's already decided to do additive manufacturing. And usually if you're looking at the prediction of whether or not to use a part in additive manufacturing, you've already zeroed in on one process. Topology optimizations, what you saw in the video there in the few slides ago, the shape, the topology of the part changing in order to accommodate the strength, primarily for powder, not power, based processes. And then Amati looks at additive manufacturing addressing both the process and material selection. So it's sort of midway. And then lastly, there's machine learning approaches that are quite a few, but they're mostly centering also into the materials and process selection. One thing I thought about, there's a lot of machine learning done with design for manufacturing assembly, DFMA, a lot of people say. And maybe some of those approaches in machine learning could be adapted to additive manufacturing theory. The problem is that you need a large database for machine learning to start learning in order to get somewhere. And there's not so much published in scholarship or in patents, which is also a place to do machine learning. They haven't occurred enough frequently, I think, for that to be effective in the part selection yet. The benefits of doing design methodology research on additive manufacturing. You can develop clear paths and definitions, and it leads to well-defined educational pedagogies, which is what I really want to talk about here. And you have clear methodologies leading to automating some of these aspects of the design process for these manufacturing processes. And I just showed you one that's already commercially available. And if we think, they're not going to do that, 30 years ago, 35 years ago when I was here, CAD software didn't exist hardly on campus. And all of the machining programming was done by hand, and a lot of it was, of course, almost all of it through experience. And now today, students who graduate go into environments where they expect to have CAD CAM to do a lot of this thinking process, and they make judgment after the initial design is finalized into the manufacturing process. As you know, there's all these different types of CAD CAM software: fit analysis, fastener selection in databases, FEA, heat analysis, flow, fluid flow, and then the design tools with CAD, tables, global variables, and so on. All of this helps with design for aspects. And these guys in particular will lead into design for additive manufacturing as well. One more example of design for additive manufacturing. This is a publication as opposed to an online commercial. And it's not as sexy looking, but you break it down into designer-driven and process-driven types of approaches. Designer-driven is geometric fit of a bracket that's going on a rocket launcher, and then process-driven is the stress analysis and weight analysis side. And you can see this nice fancy flow chart, but this is how a lot of the methodology development for design for aspects of research occur. And you start up here with the rough model idea, and you work all the way through this, and eventually you come down to, can you do your work? Notice that in here, there are 2 software packages mentioned, and NetFab is a software package that's now integrated into Autodesk, and Magix, I forgot the company for that, but they both try to do similar things, but they don't quite line up. I would say mesh up, but that's sort of a pun for CAD people and for people working in this area. But nevertheless, the software is there, but it's not connected, it's not whole. And so there's a lot of discussion on how to make the software work, and you drive a lot of your work and thought process into the software, and then you still have a lot of work to get it to your final production. This is what it looks like visually going through the steps using the AutoCAD software, where you have your structural analysis. A lot of you have probably seen this, where you have sort of a web structure that tries to reduce weight. The designer comes in and says, I'll make that more organized, and then further organization, and then finally comes back with a final design with a new concept of a rib structure. And honestly, that construct is made from other software that is available to them. And then that goes into the machine. So with the motivation, here's the education development side of it. M4D, education. The term manufacturing for design, as opposed to design for manufacturing. Manufacturing for design originated in 2014 with an NSF workshop report. And the fundamental statement was engineers will need additive manufacturing as part of a fundamental knowledge base, just with milling, casting, molding, etc., if you're going to make products as an engineer. And Chu, later in 2016, used the term MFD for manufacturing for design to discuss hybrid manufacturing and smart factories with additive manufacturing fundamental to those. And those are basically associated with configurable manufacturing facilities involved with making one-off or limited run products on the fly. Now, another motivation for M4D education is that most students come to college knowing something, and I'll put that in quotes, about 3D printing, but knowing very little, I've discovered, at least out west. Most students coming in engineering, I'll say most, do not know much about traditional manufacturing processes. They haven't had shop or high school fabrication, metal shop or wood shop. Most of them didn't have it at their schools. Now, this is prominent in Arizona, Nevada, and California, where my students came from. I've heard some of that happening in Tennessee. Maybe it's not as prominent because there's still small manufacturing and big manufacturing in Tennessee, I think. But nevertheless, when I was coming out of high school many years ago, many decades ago, I had both shops, and I was an A student, but I was expected to take shop on both sides because that's what you did if you were going to be an engineer. Today, students have 3D printers, and they have them everywhere in their facilities, their high schools, and they at least know how to push the buttons. And the problem is that's about all they do know. But we can leverage that knowledge that they have, the familiarity, into having them learn traditional manufacturing processes as part of design. So my educational approach for M4D, if I can get funding for this, I really would, is to have a class, or even classes, but certainly a class, that has integrated engineering technology as part of additive manufacturing. So you start with additive manufacturing, and then you'll grow out of that the fact that there's an extrusion technology there. And so you discuss extrusion and injection molding technology. There's also an aspect of material selection as part of metal sintering or metal melting. And so you can bring in materials engineering to that aspect of the studies. There's controls associated with the system. That's mostly associated with polymers, but also it can be a part of the controls associated with powder bed metal technology. There's programming involved with any of this, so we can bring in coding, and they learn that early on in their programs. And of course, there's machining it's a little bit of a stretch for this one, but given it's got controls and perhaps at least for polymer manufacturing, a gantry system, we can branch off into machining. Also, there's some advanced additive manufacturing processes that have machining as a post-processing capability. So I'd like to wedge that in there because it's pretty prominent in what we'd like to learn. And that right there gives us a nice fundamental for an undergraduate. All of these different technologies combined with additive manufacturing. The students will learn that additive manufacturing is part of the traditional manufacturing methods available to product development. Not that it's the only thing you push a button for. The goal is to get them to understand that they need to select an appropriate technology for the design situation. You don't always 3D print. Students will also hopefully learn as part of that the capabilities and limitations of all these manufacturing methods, not just additive manufacturing, but the other ones as well. Students then the goal is to have them demonstrate an understanding of the need for clear specifications in the design process so they can make clear decisions as to which manufacturing process to design for or choose. That's my system engineering coming out there. There could be campus objectives too for this type of class. You could bridge across multiple multidisciplinary programs, multiple engineering disciplines certainly, and tie it into additive manufacturing. Ultimately, any undergraduate could take this version to try out. If we made it at the freshman level, we'd have to scale it back in terms of the knowledge level required, but it could be an introductory course. I don't know the terminology used at the university yet, but sort of an open elective. If we had the bandwidth to offer it, it would be probably, I hate to say this, a class fees money generator, because a lot of students like to try this class if you set it up properly for the basic requirements for entry into any program on campus. It'd probably overwhelm us, I would say. We'd probably have hundreds of students take this. And then the bigger picture would be to translate this education process into integrated additive design methodology research. More educational development ideas, MSEM. I've talked about this a little bit with my department chair, but at some point developing some limited electives and program options coming out of general engineering, the general engineering context. Could be at the mid-level, upper level. I've got an idea for something else I'll mention next slide at the graduate level. And possibly, will MSEM, can the engineering management program itself, if there's enough interest, possibly grow into a research-oriented branch, either affecting into engineering management or with these electives into systems engineering. Don't know, I won't be in charge of it for sure, but I would like to support that if people want to look at that. I'd like to help with that idea. And then certificate programs, this is sort of a hot one, but they're out there. And Northern Arizona University, Arizona State was big into it at the time because they're big in everything because they're big. But certificate programs, in general, can we offer them in a, excuse me, sorry, I do this every time because we've been talking about it in Northern Arizona quite a bit. But Tennessee Tech, can we offer some of these here out of engineering? Can they be of sufficient quality that they could translate into undergraduate or graduate courses for some of the classes? Can you bundle them into 9-hour packets or 18-hour packets in specialty areas so that they could be certificates from Tennessee Tech? I can go into the discussions about why that is or is not of value some other time, but it's something we could look at as we get more into online courses. Now, I have an idea for a graduate level course. This could also be a senior course elective initially, and then a graduate level course. But I would call it Additive Manufacturing for Applications. And I stick my 4 in there again, AM4A. Basically, the system design side that I noted early on. It's the not the theory, but the practice of what we do now in planning for additive manufacturing of products. It would not be laboratory based. It would be nice to have a lab associated with it, or at least a demonstration aspect of it, but it doesn't need to be lab based. Eventually, I plan it to be online for the last bullet down there, but it would discuss and present current state-of-the-art industrial additive manufacturing, cost evaluations for products and how you determine what should be additive manufactured and what should not be, and go to other systems, applied topics of design for additive manufacturing methodologies, some things I showed you there about weight distribution or weight reduction and strength analysis, not necessarily doing the strength analysis completely, but what are the options you have if you've got a problem. Design planning and manufacturing constraints. Design planning, because as I mentioned early on with my Rapid Lab, I have learned the big time is in planning for the manufacturing, doing the design work. And the more exotic the manufacturing process, the more new the manufacturing process, the longer it takes to do the design. Manufacturing may be shorter, but the design takes longer. And then manufacturing constraints. You can make one product for a given hour, let's say, of cycle time, but then you make 3,000 products like that GM part, it still takes an hour apart. You can bundle things up and reduce that some, but it's still mostly an hour apart. Whereas if you do traditional casting or some other methods, it gets greatly reduced. Actually, casting's not that much different. But you do other processes such as injection molding, and that cycle time goes way down once you make the mold. So the mold also ties into doing cost evaluation. And if there's enough interest putting it online, there could be a professional certificate and have industry come in and take this course as a standalone course. So that's sort of my research ideas and applications, and I was hoping I'd finish early. I think I did. And this is not a publication, but I really liked it when I was looking it over. And I actually saw it for the last time today. I want to make sure it's still here. But that was that bracket I was looking at that shrunk things down to its final shape. And I'll just say it word for word. We're focused on production opportunities where we can provide a business value for GM and for the customer. And then this last one's excellent. For us, it's not about what you can do. It's about what you should do. And so that relates to design for additive manufacturing the way I see it in the system development side. The part of the development process is evaluate whether you should do it before you actually do it. So in summary, I talked about my fundamental research ideas I'd like to do, and then engineering education, and what I'd like to do as well, a little bit on the research side and implementation. So with that, you all were really nice, didn't say anything. I thought this was a nice way to end. The home on the left was the home I finished leaving and vacating in Arizona. You can even see the mountain in the distance over here. And then here's my new home in Cookeville. And it is equally beautiful in a different way. And we all have transitions, and it's really exciting, a little stressful, but it's really interesting just going from one place to another and just learning new things. And so with that, I've finished my presentation. If you all have any questions, I'll be glad to address them.
Thank you very much. Appreciate it. Definitely fascinating pictures at the end and very interesting videos in the middle. So we'll open the floor to questions, and please turn on your video and mic and ask a question or two or more.
Whoops. Discard that and then stop my sharing if anybody wants to. I guess I should keep sharing, probably.
It's up to you. If yeah.
I'll stop sharing. I can bring it back if someone wants it back.
Absolutely.
So I'd like to start things off with a question, if I could.
Sure, please.
So,
and
John,
you can turn on your video if you want, Dr. Wilson.
Sure, sure. One thing that's always been very important to me is something you mentioned, is the fact that a lot of times today, particularly college track students, are not that versed in manufacturing. You know, like you, I'm a kind of a similar time frame as far as when I was in high school, and taking vocational courses was even in my time was not very highly looked upon. So I have been working on the idea of an introduction to engineering design course that's really a freshman level course, and I kind of want your thoughts at least about what you did at Northern Arizona, you know, in terms of that. I'm assuming in some ways that our student populations were actually similar in that regard to their exposure. You're new, so in terms of tech, do you have a sense that that the population here at Tennessee Tech is likely going to be very similar as far as maybe a lack of understanding about manufacturing?
Well, I will say that with COVID-19, I haven't met anybody. But I will say this, there's one way in which it's really different compared to Arizona. Arizona had a really significant portion, Northern Arizona in particular, of Native American students. Now, significant in engineering is different. Significant means in the multiple single digits, like 8%, I think is what we had in terms of our student population in engineering across the board. And so that was a unique aspect, and they were really proud of it too, because it was so close. Their education was really poor. They just did not have an ability to have technology taught very well in the remote locations across Arizona, New Mexico, Nevada, and so on. I would think that another aspect of education here is I don't know. I think that students here, being from Tennessee, I guess I can say this with some prejudice, so watch out, is that I don't think Tennesseans as much look down upon manufacturing as a career, as working in manufacturing, as significantly the population versus probably the West, working with your hands. So I think we'd have an advantage there. I'm not sure the high schools are any better equipped to do, I just don't know, do manufacturing education in the, shop education in the high schools. I've got 2 data points, and that's my niece and my nephew, and that's about it. And both of them say that they didn't have any shop offered to them at all, none. But they had a lot of computer classes, a lot of it. Most of it, they say they just used it, they didn't really understand it. And then they had these first competitions, which are with the Legos and robots, and I've had some experience with that as well. But only a few students exposed themselves to it. I tried doing some outreach. You saw early on that, bringing automation, Lego robots, and also the Baja vehicles that I used to advise. We had the first few come out, and I actually dragged them out there with my truck and unrolled them onto the dusty outdoors and rolled them into the gym, and we talk about the design process for those vehicles. They liked that. But it was pretty woeful, the preparation I had there. I don't know about here. I spent 5 minutes saying I don't know. Sorry about that.
That's good. That's good. The other question I had, and that's all I've got, just these 2 questions, is really what you think overall the potential of systems engineering has in terms of a research field and really a higher ed field as well. Not just degrees, but certificates or undergraduate minors or master's degrees. So what do you think the potential is for systems?
I've got a lot of ideas on systems. The irony is I wasn't allowed or able to do much systems engineering education back at NAU because once they saw that I could operate a mill, they really put me on manufacturing processes instead. They knew they needed that. System engineering as an undergraduate program, I think, is difficult except introduced at the highest levels, maybe junior, senior level. Students, from my perspective, system engineering is a modeling and simulation context. What are the requirements? How do you set up functionality of a system and design and exercise it to see what the best performance of the system will be? In fact, in my MSEM class, the EMGT 6100, I just finished with a case study on the students gave a paper on the 7 definitions of system engineering. The guy used machine learning, of all things, in papers to figure out what are the definitions of system engineering. And I told them, pick one and explain it. And so it can mean a lot of things to different people. So one thing is to, if you're going to do it at any level, identify what your system engineering is. Don't do it all at once. For me, it's systems, functionality, simulation, and optimization. For someone else, it could be logistics and management. That's certainly a part of system engineering. Graduate level research, I don't know how much the scholarship would be in fundamental research, but there probably would be a lot of consulting. And I don't really know how that bends in university systems one way or the other. You can pull the consulting into research projects on campus. But to give you an example, I was aiding a power systems simulation research project with Dr. Acker at Northern Arizona before I left on charging personal electric vehicles at night at home as more and more people have electric vehicles, how does that affect the power grid? And that's unique to each state, at most each region. And so Tennessee is going to go through that as well. And they have unique aspects, especially TVA sitting around. So that's a neat place to do either research and or consulting. And having a group of graduate students getting system engineering degrees would be really helpful for that, but they've got to have system engineering research, not system engineering management, which is what system management, engineering management, which is what we're doing now. I mean, I'm not disparaging system engineering, I'm not disparaging MSEM. It's a needed program, but to do research, you need to have students researching in that area. So you need at least a master's level, if not PhD level, to do that research for the university.
Thanks.
Thank you. Any other questions? I know that you mentioned hands-on work and interest in it. And of course, manufacturing has been changing. So a lot of people do realize that there is, future manufacturing, even current manufacturing is very different, right? It's not necessarily the old dirty environment, although some of that has to happen and will continue to happen. But everything has become cleaned up quite a bit. But, a lot of times additive manufacturing, as you talked about, 3D printing and so on, including metal 3D printing, which we are trying to develop, are very different than the traditional casting and this type of manufacturing. So there is a change that has happened across the country, I think, in that. And I think while our local high schools may or may not have shops, and I don't know it for sure either, but certainly they have 3D printers, right? And so their students are getting more into it. And we do have, as you know, a manufacturing engineering technology program as well that has a foundry, which is very unique, that there are only 2, I believe, existing active foundries in universities. Only a few and 2 that are maybe in the state. Or
Wow,
we may be the only one. So we are very unique in that. I know there was 2 probably, but maybe it's just us now, but I don't know. So foundry work is something that we are certainly, have had years of experience and some reputation there. And so, I know one of our faculty who I think is online is working on metal additive manufacturing, but using welding. And we have others who use metal. So there's a variety of things going on, and certainly some of the discussions we had about certificates, I think, is very interesting because developing certificates, it's another way of really engaging with industry, where students may not have the ability or time really to come and do a full degree, but they might be able to do a certificate, whether undergraduate or graduate level.
I will say that one of the things I wanted to emphasize was that even though I say it's designed for additive manufacturing, I really want to emphasize the entire gamut of manufacturing processes. But additive manufacturing needs to now be in that list. And
Right.
That's really it.
Yeah. Very good. All right. Any other questions from our audience? Well, if not, then I'll thank you again, Dr. Tester, for your thought-provoking presentation and very interesting discussion about manufacturing as we know it now and in the future. Thank you again. All the best.
Thank you, everyone, for sticking around.
Thanks so much, John.